Hello and good morning, dear students. Now we are solving solved problems on chapter number 3. There are 4 problems. So here in this problem number 1, there are 2 sub problems. So these are 2 problems. This is third problem and this is fourth problem. I already written all the problems. Now we start with problem number 3. Okay. So we are first of all solving 3, 2 and lastly these 2 problems. So problem number 3. What is that? A particle of mass 1 gram with velocity 2 into 10 raised to 3 meter per second incident on a particle of mass 2 gram which is at rest and scattered along direction making angle 45 degree with the incident direction, and 2 gram particle is recoiled with an angle of 30 degree. Full stop. Find velocity of particle of mass 1 gram after collision. So first of all, let m1, which is incident particle having mass 1 gram, okay, and m2, which is target particle having mass m2, which is 2 gram. Now angle of this velocity of incidence is u1, okay, for first particle. That velocity is 2 into 10 raised to 3 meter per second, okay, and u2 second particle which is at rest, okay, and angle we have given angle of scattering as 45 degree and angle of recoil, okay, or you can say that angle is alpha is 30 degree, okay. Now we have to find out velocity v1 of first particle. Now situation can be shown diagrammatically. All this is given quantities, so diagrammatically you can show m1 is incident with velocity u1 on m2, okay. Now this is before scattering. After scattering, m1 v1 and m2 v2, okay, this angle is alpha. So by using conservation of momentum, okay, we can find out that velocity. So by using conservation of momentum, so using conservation of momentum, we can write, or you don't know that. So by using conservation of momentum, what is momentum before scattering? m1 u1 along x-axis, okay. So if you take, this is along x-axis, this is along y-axis. So along x-axis momentum is m1 u1 is equal to, on the right hand side, momentum after scattering of this is m1 v1 cos theta plus for this m2 v2 cos alpha. This is the first equation. Now next equation is along y-axis. You can write momentum before scattering is 0 and after scattering is m1 v1 sin theta is equal to, see, m1 v1 sin theta, okay, this component is equal to m2 v2 sin alpha, or 0 is equal to minus m2 v2 sin alpha. So this can be written as, okay, if you take this term on the right hand side, m1 v1 sin theta is equal to m2 v2 sin alpha. So from this equation we can write v1 upon v2, v1 upon v2 is equal to, see, v1 upon v2, if you take this term on the left hand side, so v1 upon v2 is equal to m2 upon m1. Okay, so we have to take this term on the right hand side, sine alpha divided by sine theta. So call this as equation 1. Now divide equation 1 by m1. Okay, so dividing equation 1 by m1, we will get, okay, m1 is gone, so here and here, if you divide by m1, we will get this. Now in this equation, if you take v1 as common or v2 as common, so in the first term we have v1 upon v2 cos theta, plus here if you take v2 as common, we will get m2 divided by m1 cos alpha. So now this equation can be written as u1 is equal to v1 cos theta, okay, plus, sorry, this equation u1 is equal to v2 multiply by v1 upon vt or v2. So v1 upon v2 can be written by this equation, so m2 divided by m1 sine alpha divided by sine theta, okay, multiply by cos theta, okay, plus m2 divided by m1 into cos alpha. So here we can take m2 upon m1 as common. So here cos theta upon sin theta is, sin theta upon cos theta is tan theta. So this is equal to this. Now v2 is equal to, from this equation v2 is equal to, okay, so call this as equation number 3. Now from equation 2, v2 is equal to v1, okay, multiply by m1 upon m2 sine alpha upon sine theta. If you put this term over here, okay, so put in 3, you will get u1 is equal to, here v2 is equal to v1, so m1 upon m2, m2 upon m1, this term will cancel. Again sine alpha divided by sine theta, okay, so again sine alpha divided by tan theta plus cos alpha. So if you solve this equation for v1, so v1 is equal to, now u1 divided by sine alpha divided by sine theta in bracket sine alpha divided by tan theta plus cos alpha. So by using given values, u1 is 2 into 10 raised to 3 sine of alpha, which is sine 30, divided by sine 45, multiply by sine 30 upon tan 45 plus cos 30. Okay, if you solve this on calculator, you will get 1.04 into 10 raised to 3 meter per second. So this is the answer for our given problem number 3. Now we are solving problem number 2. Okay. So problem number 2 is I already written over here. Statement of problem number 2 is this: a particle is elastically reflected back from rigid plane which is in uniform motion. Find velocity of particle after reflection for arbitrary angle of incidence. Now, diagrammatically, so solution of problem number 2, diagrammatically, if particle is having mass m, p1 is initial momentum of that particle. Okay, so that particle, I think here, for arbitrary angle of incidence. So suppose this is the plane and this is the particle which is incident. Now if m is the mass of particle, now since this, if you take angle of incidence as theta here, or you can choose theta as this angle for our simple calculations. So this is before scattering, and after scattering, since it is elastically scattered, plane is moving like this. Okay, and particle is again reflected backward elastically. So this angle is again theta. Now here plane is moved like this, plane is like this. So this is plane. Okay, so this is the plane which is moving. Particle is initially incident on this and reflected backward. So this vector and this vector are opposite to each other. Suppose P1 is the momentum before scattering of particle 1 and P2 is the momentum of plane before scattering. Here P3 is momentum of particle after scattering and P4 is momentum of plane after scattering. So we can apply law of conservation of momentum since scattering is elastic. So by using here P1 is, you can write momentum of particle before scattering, P2 is momentum of plane before scattering, P3 is momentum of particle after scattering, P4 is momentum of plane after scattering. So by using law of conservation of momentum, we can write momentum before scattering, which is vector P1 plus vector P2 is equal to vector P3 plus vector P4. Okay, so call this as equation 1. Now we can take, this is x-axis and this is y-axis. So we can write all those equations along x and y-axis. So along x-axis, see, so by using conservation of momentum along x-axis, so component of this vector is this. So P1 sine theta plus P2 is momentum before scattering. Okay, so after scattering, component of this is minus P3 sine theta. See, component of this vector is opposite to this direction. So minus P3 sine theta plus component of this is P4. Okay, so from this equation we can write P3 sine theta minus P3 sine theta is equal to P1 sine theta plus P2 minus P4. Okay, we have to take this term on the left hand side. So call this as equation 2. Now along y-axis, if you apply conservation of momentum, so before scattering along y-axis, this P1 is having component downwards. So minus P1 cos theta, component of this is 0 along y-axis before scattering, and for this along y-axis component is P3, okay, instead of sine theta, we have cos theta. Okay, plus again component of y component of this P4 is 0. So P3 cos theta is equal to P1. So from this equation you can write P3 cos theta is equal to minus P1 cos theta. Okay, now call this as equation 3. So in equation 2 and 3, here we have minus P3 sin theta, here we have P3 cos theta. So we can square and add equation 2 and 3. So squaring and adding equation 2 and 3, we will get P3 square sin square theta plus P3 square cos square theta. So we will get P3 square is equal to, on the right hand side, P1 square sin square theta plus this square P1 square cos square theta. So this is nothing but P1 square plus P2 minus P4 square, okay, plus 2 times P2 minus P4 into P1 sin theta. Okay, so P3 is equal to square root of this term, and P3 is m into V3. Now V3 is the velocity of particle after scattering. So V3 is equal to 1 upon m into this. So this is the equation for velocity. Now we are solving problem number 1. So here in problem number 1, we have actually two problems. So show that kinetic energies of final states in laboratory and CM frame are related as T lab is equal to TCM plus 1 half M1 plus M2 into V square, and TCM is equal to M2 divided by M1 plus M2 T lab. So T lab means kinetic energy in laboratory frame, TCM is kinetic energy in center of mass frame. So final state of particle can be shown as, okay, see, m1 is incident with velocity u1 on particle m2, which is having initial velocity 0. So this is before scattering, and after scattering, vector v1 is the velocity of m1, okay, and vector v2 is the velocity of m2. So this is capital V, velocity of center of mass. Okay, now here this vector is v1 dash and this vector is v2 dash. So this angle is theta, this angle is alpha, and this angle is theta dash. So now in laboratory frame we have velocity v1 and v2. In center of mass frame we have velocity v1 dash and v2 dash. Now here on the left hand side we have kinetic energy in laboratory frame. So kinetic energy in laboratory frame as 1 half m1 v1 square plus 1 half m2 v2 square. Okay, now this is equal to 1 half m1. So v1 square can be written as vector v1 dotted with vector v1 plus 1 half m2 v2 square can be written as vector v2 dotted with vector v2. Okay, now call this as equation 1. Now vector v1 dotted with vector v1. So vector v1 here can be written as, this is vector v1, which is vector law of addition. By triangle law of vector addition, this vector can be written as vector v plus v1 dash. Okay, so v1 dotted with v1 is equal to, so we have to take dot product of these two vectors. So that is v plus v1 dash dotted with v plus v1 dash. Okay, now this is equal to, what is that? So capital V square plus V1 dash square plus next term is capital V dotted with V1 dash plus V1 dash dotted with capital V. Since A dot B is equal to B dot A, that is nothing but 2 dotted with V plus V1 dash. Similarly, if you take V2 dotted with V2, now that becomes on the similar line, you have to solve this vector V2 as you can write vector V2 as capital V plus V2 dash. Okay, capital V plus V2 dash. If you solve this, you will get V square plus V2 dash square plus 2 times vector V dotted with V2 dash. Okay, so put in equation 1. So we will get kinetic energy in lab frame is equal to 1 half m1 into v square. Now v1 square can be written as capital V square plus v1 dash square plus 2 times vector v dotted with v1 dash plus 1 half m2 into v2 square. Okay, so v2 square is again v square plus v2 dash square plus 2 times v dotted with v2 dash. Okay, now this is equal to, so here you can take 1 half common from both this, m1 plus m2, and here that is capital V square. Okay, so T lab is equal to plus next term is what, 1 half m1 v1 dash square plus 1 half m2 v2 dash square. So that is nothing but kinetic energy in center of mass flame plus next term is 1 half m1, okay, multiply by v plus v1 dash. So this 2 will get cancelled. So vector v dotted with m1 v1 dash plus m2 v2 dash. Okay, so I will left you this as an exercise. If you solve this term m1 this term and 1 half m2 this term, you will end up with this term. Okay, but for center of mass system this is equal to 0. Okay, so here since this is equal to 0, we get this equation. Okay, now with this we finish our this section. Now second section, so for that we can write by conservation of momentum before scattering is m1 u1 is equal to momentum after scattering, which is m1 v1 plus m2 v2. Now this is equal to, you can write vector v1 as v plus v1 dash, okay, and vector v2 as v plus v2 dash. So this is m1 v plus v1 dash plus m2 v plus v2 dash. So this is equal to 1 half m1 u1 is again this is nothing but m1 plus m2 into capital V, and we will get plus m1 v1 dash plus m2 v2 dash. Again that term is 0. So here capital V, which is velocity of center of mass, is m1 divided by m1 plus m2, okay, into u1. So here you can put this term in equation 3. So if you put that in equation 3, we will get kinetic energy in lab is equal to 1 half m1 plus m2 into v square. So that is m1 square divided by m1 plus m2 square into u1 square. Okay, and plus kinetic energy in center of mass. So this term is 1. Okay. So again, this is equal to now 1 half m1 u1 square is nothing but again kinetic energy in laboratory frame. Okay, and multiply by m1 divided by m1 plus m2. Since here we have m1 square, 1 m1 is written over here. Okay, now TCM is equal to, if you take this term on the left hand side, so here T lab we can take common, so 1 minus m1 divided by m1 plus m2 into T lab. Now this is equal to, if you do cross multiplication, so m1 plus m2 minus m1, so in the numerator we have m2 divided by m1 plus m2 into kinetic energy in laboratory frame. Okay, so this is the proof here. If you asked in exam this, you have to solve all the way toward here. If you asked only here to here, you can show that up to here. Okay, now this with our third chapter is finished.